So, thank you very much. So the goal is talking about type-driven development. Let's say that we want to implement this type signature. This is a Scala signature based on algebraic data types. And following the method of type-driven development, we can come up with an implementation of this signature. So the idea is how to automate this process. In order to automatically generate this, the program for this signature, we can use logic. And the standard way of using logic for this purpose is translating the signature, the Scala signature, into a Sequent. Okay. Okay, it's translating this Scala signature into a Sequent, a logical Sequent, and then attempting a proof in the Sequent calculus for this Sequent, and then based on the proof for the Sequent calculus, okay, then we will translate this proof in the Sequent calculus into a proof in the natural deduction calculus for intuitionistic logic, which is equivalent essentially to the simply typed Lambda calculus. And then when we have this abstract program, then we will be able to translate into a Scala using macros, for instance. Okay? So this is the standard approach, and the idea for this talk is to show the role that algebras and co-algebras can play in the implementation of this pipeline, the implementation of this process, okay? How can we model, how can we implement these translations of proofs and generation of proofs in terms of unfolds and in terms of folding, in terms of catamorphisms and anamorphisms? Why? Why is this interesting after all? Well, I think that it is interesting from the point of view of showing an example of using these co-algebraic techniques for a particular example, because I think that this algebra and co-algebra stuff is worth knowing, okay? How many of you have heard about co-algebras? Okay. So this is, I think that this is an interesting example, and it will shed some light into what is type-driven development and how can we formalize this fuzzy concept, okay? So before diving into this co-algebraic stuff, let me recall briefly the main concepts in this picture. So let's start with type-driven development. In type-driven development, what we do basically is to implement a program for a given signature step by step by refining some holes in the program. These holes are represented by these triple question marks, okay? And for each hole we have a type, so that the whole development is driven by the types of this hole. So in this case, what we have to do is to implement this function that given a function from either A or B to C, we have to generate two functions, one from A to C and another one from B to C. Okay, how do we create such a program? How do we fill this hole? There is only one option. The only option here is to use Lambda expressions, which are the constructors for functions. And then what we have to do, we have another hole. And this hole is a tuple, is a product. So we use the constructor for products. And again, what we have are two holes, and these two holes are function times. Again, we use a Lambda expression. Now we are stuck. Why? Because now the types of the holes are a variable, a type variable C, a type parameter C, and we do not have constructors for C. Okay, C could be any kind of type. So our only chance now of filling this hole is to use the information that we have available in scope. Okay, so in scope we have, for the first hole, we have variable f and variable a, and the types of these variables will drive us towards our goal. So, for instance, in this case, the type of f, of variable f, is a function that allows us to obtain c, values of type c. So we use this function, and we will be able to obtain C provided as far as we find a type, a value, an expression, a program of type A, either A or B. Okay. Now we have to use the constructors for either, and we can use left or right, and we choose wisely, then we'll be able to complete our program. So in this type-driven development style, what we do is proceed step by step by choosing a constructor or a destructor for a table of constructors or destructors of our type system. In our case, algebra data types come with the constructors and destructors for function types, for products, for sums, and so forth. Okay. Now, how do we automate this process? How can we make this process automatic? What we do is to translate this signature, this Scala signature, into a sequence by using this correspondence between propositions and types. So either the sum types are disjunctions, the products are conjunctions, function types are implications, and so forth. So we can come up with this sequence. This sequence has two parts. In the left part, what we have are the premises, are the information that we have available. In the right part is the type that we have, the proposition or type that we have to prove. And then we will use the sequent calculus. The sequent calculus is structured in terms of a number of rules, left rules and right rules. The right rules will allow us to create, to prove conjunctions, disjunctions, and implications. And in the left rules, what we have is the rules that will allow us to infer some information from implications, from disjunctions, and from conjunctions. Okay? We will see an example now. So this is the sequent, the argument that we have to prove. We have to prove an implication, which is how can we prove this sequent? Of course, using the right implication rule. Then we have to use the right conjunction rule. Then we split the proof in two parts, and then we have again to use the right introduction rule and so forth. Okay, and now this part is important. Okay, because what we have now to do is to exploit information from the premises that we have in the left part of the sequence, and what we see is that we have an implication, and from this implication we can obtain C. The rule, the left implication rule says, okay, you will be able to obtain C as long as you are able to prove the antecedent of the implication, and then prove the consequent of your sequence using the consequent of the implication. And this, of course, you can do it because you have information. You can use the actions, okay, here and here. Okay, so this is a proof in the sequent calculus, and what we have to do now is to translate this proof of the sequent calculus into a lambda term, into a lambda expression, into a program based on algebraic data types, okay? And how do we do this? We do this using this kind of translations, rules which are labeled with the procedure in order to come up with the lambda expression. Okay, for instance, for the left implication rule, if we have a proof, we have a term, a lambda term, okay, for A, for the antecedent, and we have a lambda term for C, for the consequent of the sequence, which is depends on X, okay, which was a new premise. What we do is to substitute X for the application of F to T. Okay, so these are rules. Okay, this is a procedure for each rule in the sequent calculus. What we can do is to analyze the proof of the sequent calculus, okay, step by step, and come up with okay, the Lambda expression that we want. Okay, I don't have time in order to to explain clearly which are the details. How do we obtain, okay, this Lambda expression? But the idea is that from this Lambda expression, we can come up with the Scala macros with this code. But the idea, again, of the talk is showing how this process of transforming this proof tree in the sequent calculus can be transformed into a Lambda expression using catamorphisms, using a fold, and how the generation of this proof tree in the second calculus can be generated, this type-driven development process can be generated by unfolding a seed, a sequent, okay, using a specification, a co-algebra, okay? So this is the idea of the talk. So we will start by explaining first the fold part, which I think it is the easier part, okay? And then we will go into the co-algebra part. So in order to implement this idea, okay, what we had to do is to implement the sequent calculus, okay, the sequent calculus LG, which is the name, the specific name, the proper name for this sequent calculus. And we can, of course, to implement NG, okay, the natural deduction calculus. And in order to do that, what we will use is an encoding. We had to choose an encoding. So we are implementing a formal calculus, a logical calculus, a sequent calculus, but this is nothing else but a language. Okay, so what we had to do is to implement a DSL. And in order to implement a DSL in a Scala, we had to choose our technique. And the technique that I chose here is tagless-final, an untyped implementation of the sequent calculus, right? So for each of the rules of our sequent calculus, what I have is an entry in this type class, and the proofs are this charge encoding of the algebra. Basically, what we are doing is implementing an algebra using the type class, okay? Using this algebra, this type class, we can represent the proof tree that we saw before as follows. Okay, in a very direct way. We do the same for the simply typed Lambda calculus, for the NG natural deduction system. Okay, and now the idea of translating this proof tree into the natural deduction proof system into the simply typed Lambda calculus is simply an instance of the type class. Okay, and this is in a very direct way the same specification that we have in our logical method, right? So this is the first part. We can very easily model as a fold, as a catamorphism, this translation of the proof tree, okay, in terms of a Lambda expression. But now, in order to talk about the reverse process, how to generate the proof tree, okay, what we have to do is to change a little bit the representation. Right? Because instead of using type classes for embedding our sequent calculus language, what we are going to do is to use F-algebras. Okay? And F-algebras is simply representing algebras, but using a functor. Okay? And this functor that you see here, as you can see, is very similar to the type class representation. The difference is that instead of using methods for each of the rules of the sequent calculus, what we have is a case class, okay? And we have a sum type for the different variants of the functor, okay? For the different rules. And now an algebra is simply this function, a function, okay, from the functor of t to a t. What does this algebra say? Okay, this algebra, what it says is simply, is a procedure, is a rule in order to transform a layer in the expression, in the proof tree, using a value t, whatever is t. Okay, so this is important. In using this functor, what we can do is to represent the proof in this way, using this fixed recursive data structure. Because the idea is that the functor represents a layer, right? And the whole tree is a stack of layers, right? So that the algebra, what it tells us is how to remove, how to transform a layer using, for instance, a lambda term or whatever thing, right? And this idea of, okay, don't know what is happening here. I will.
Go ahead. Let's go.
Okay. So this idea of implementing our proof terms in terms of this functor is this one. Is that we have this functor, and it will allow us to talk about not only catamorphism but also about anamorphisms. Anamorphisms are based on these functions. These functions, if you notice, they are reverse. Okay, an algebra is from the functor to a t. In the case of the co-algebra, what we have is the reverse. Okay, and in the reverse, what we have is how to generate a layer in this proof tree based on a seed, right? And this seed will allow us to generate, if we unfold, okay, this process will allow us to generate all this proof tree, right? And this is the idea. And of course, we will use as seeds the sequence, an implementation of the sequence. And in the sequence, okay, what we have will be an co-algebra of this structure. Given a sequence, in type-driven development, all the processes driven by types, by the sequence, okay? So given the sequence, what we have to do is to generate a layer of our proof tree. But this function can't be implemented in this way. Why? Because given a sequence, it is not necessary that we have a proof tree for that sequence. So what we have to do is to at least to acknowledge that we can fail in this process. But this is not satisfactory either, because we may have several options, right? So using this implementing, okay, this co-algebra, this signature, okay, what we have is the possibility of unfolding and implementing the whole search space for the different proof trees of a given sequence, right? And this proof tree might be infinite, of course, because we can have infinite branches. And so the idea now is that we have to search over this search space in order to find the finite proof trees that satisfied our type. And with that, we can implement our process of finding automatically a lambda term, a lambda expression with algebraic data types for our signature in terms of unfolds, a search strategy, because we had to navigate somehow this search space that we generated by unfolding the sequence, okay? And finally, folding over this proof tree in order to find our program. So, in conclusion, what we saw is that we can understand type-driven development as exploring this search space that was generated by unfolding a sequence that we generated from a given signature, and then searching over this search space, okay, and then folding once we have the different proofs with a particular algebra, okay? And I recommend this paper, okay, this talk by Alessandra Silva at Popel, because it pays a lot of attention to functors. Functors is the key, okay, for this embedding and for talking about algebras. And she shows that functors, with functors we can derive the syntax, we can derive the operational semantics, we can derive many things. And what we show is that through functors, with functors, we can also derive this method for finding proofs of a given type, okay? Also, it is important that to come up not only with functors, but with higher order functors, okay? Because in the embedding that I showed, this embedding was untyped, okay? But if we implement the typed version, all the information in the sequent calculus rules will be there, and then we will be able to automatically derive this co-algebra for obtaining the search space. Here you have another reference, which is really nice about how to implement this, not exactly with functors, but with this idea of typed embeddings, okay? And then there are other aspects that I would like to investigate, because this approach is general. We can do this for any kind of sequent calculus, for classical logic or for linear logic and so forth. And so this is a framework for studying and for experimenting with the embedding of proof systems and with type-driven development for different kind of languages. Okay, and there are also some connections to property-based testing, because after all, in property-based testing, the generators, they aim at finding some terms of for some types. Well, we are doing exactly the same. What we are doing is to find proofs for some sequence, and these sequences are the types, okay? And then there are some relationships to dependently typed grammas and so forth. You have the code and the slides at this branch of this repository. Okay, this repository also has the implementation for macros, okay? We didn't talk about macros because of lack of time, but you will find there the macros. It is not exactly updated in the latest version, but in this branch you will find the code that we have here. So see you at Lambda World, at the Scala meetup group in Madrid. Okay, and thank you very much for your attention.